Hello, this is David D. Hilster, and I am a critical thinker, dissident scientist. I'm here to tell you the truth about science, something the university professors won't tell you, at least most of them, something here the mass media won't tell you, and certainly those science evangelists, they certainly won't tell you. And here I am with my great friend and dissident expert, Mr. Greg Volk. How you doing, Greg?
I'm doing great. Great to talk to you again, David.
Yeah, I mean, it's great because now my father's starting to make some noise out there slowly. He's got like 45 subscribers now. It went from,
Awesome.
yeah, and then we got Nick Percival talking about, of course, special relativity and time. And he's, if you guys haven't seen his stuff, he actually fought for a couple of years. I'm trying to get that on tape. He actually was writing the Einstein Institute in Germany for years,
Hmm.
painting them into a corner. I
Yeah.
really want to hear that. I told him, I said, you should just write a book about that because, he was basically, by law, the Einstein Institute has to answer questions about relativity, whether you believe it or not, or whether it's, so that is pretty remarkable. So he's got his, and he went, once I announced him, he only had like 17 people because he wasn't really doing anything. So he's
Hmm.
already almost up to 40.
Well,
So
that's
thank you
great.
very much, subscribers here. It's really worth it, and they're not all going to win awards in like keeping people awake by the way
You
they
have to be a
present.
little interested in this
Right.
stuff.
No, but it's very interesting stuff. In fact,
Can
they're
I
not too.
brag on Nick for a little bit?
Yeah, go ahead. Absolutely.
Back in 2011, I kind of helped him a little bit. He was putting together a campaign, if you will, to on the 100th anniversary of the twin paradox, which is the paradox that says that that if someone leaves in a spaceship and travels for really fast for a long time and comes back, he'll be younger than the guy that stayed here on Earth, and the reciprocity issue is the main argument against it because the guy on Earth is also, although we seem to be not moving, we're moving relative to the ship. So why aren't we younger when we
Right.
get back? And he was asking a series of questions of mainstream scientists and trying to get their, I mean, you would think if mainstream science is so well settled that everyone would agree on the answers to these questions. But the truth is, there was disagreement among the conventional scientists
Mhm.
about the answers to some of these, various questions about the twin paradox. And he was just, really on a mission to kind of have something to show for the 100th year anniversary. And of course, a lot of people just wouldn't even bother to answer his questions. But, he's no dummy. He's a Harvard grad too, just
Yeah.
like John Chappelle. So anyway, I wish him luck with the program. He's definitely spent a lot of time thinking about time. That's his
Sure, sure. And
specialty.
he's doing a lot of preparations. He says he's got
Mhm.
13 in the works. So,
That's awesome.
please subscribe alongside the channel, alongside Siri. You'll see his channel, Nick of Time, which is a pretty cool name.
Mhm. Yeah.
So, but yeah, he's out there too. And today, though, we're going to be talking about a book from one of my favorite scientists, of course, is Dr. Alexander Unzicker, who, by the way, yeah, there it is, Einstein's Lost Keys. That's his last key, right?
One key.
Key. It's only one key. Yeah. Someone else stole the other ones, but he also wrote the Higgs Fake, which is extremely brave book to write since he is a physicist and he's in Europe and he hangs out with these guys to really take it to town and said, he would throw out all of particle physics since 1930. So it's been great too because we've been talking enough about him because I've been watching his subscribers. When I
Mhm.
first started, he had about 370. Now he's over
Mhm.
400. So I think we're getting people in his way too. So I'm going to
Good
try
deal.
to hopefully get him to do some more, and he'll definitely watch this program.
Mhm.
So you said you took a read on his book
I
and you
did.
and it
It
really
actually
inspired you, yeah?
it did. It inspired me to again. As with so many things, you kind of kick around ideas for years and years, and then something comes along and sort of jars you. And actually, in my case, the thing that was the most exciting about it wasn't an idea that I read from the book, but something that the book caused me to think of. And
Right, right.
that so happens quite often. I don't know, how other people come about things, but it isn't as though you're going to get an idea from something and say eureka. It's more
Right.
like all of the knowledge that you have stored up in you, plus what comes along, suddenly creates something new, and then it's like, wow, this is exciting. So
Yeah, and I
that's
think I think I think one of the interesting things is too is one of the things I like to stress with my readers. You don't. one of the worst things you can really do is to try to read stuff that's going to support what you're always
Mm.
thinking. It's
Hmm.
always great, and I'm not saying that he doesn't, but it's always great to pick up a book. And I get books all the time. I got another one from James Carter. Keeps saying I did one. He's got another version of his book, but
Hmm.
you know, and it's got a lot of stuff very different from what I've been thinking. But there's a lot of no matter what it is, there's people spending a lot of time on this stuff, and there's always some truth in there. And
Hmm.
beyond that, there's always something that's going to stimulate you. You know, one of the, like I said, if you go outside your comfort zone, if you go into a, like I'm not an etherist, but if I read about ether or action at a distance, or you know, finite universe, which is what you're going to be talking about today, even though I'm
Hmm.
an infinite universe kind of person,
Right.
it certainly makes you think, and it's going to be a lot better than you going out and simply finding your little tribe and staying in that. And you know, that's the thing where it gets you yourself found a lot of things in common with Dr. Unzicker. Is that true? What are some of the things you
Yes,
guys
I
have in
did.
common?
I mean, I most pretty much almost entirely agreed with the things that he wrote. So that was, obviously good. But again, like you say, I don't always agree with the people that I read. So, um, that's not necessary. The important thing really is, what is reading this material going to inspire in you, and what's it going to create in terms of helping science to grow and things like that. So I guess I'll just quickly give you a summary of the book, and then I'll
That'd be
tell you
great.
why I got excited about it. And hopefully, again, I'd love to hear Dr. Unzicker reply. And I actually was planning to contact him and maybe get a dialogue going, because I have some ideas that he might enjoy too. Um, but okay, so basically, the idea that he has in there is that Einstein's and by the way, that what's fascinating, what I love about this book is, sometimes people in the NPA were known as the Einstein bashers, and as if to say everything Einstein ever wrote was horrible, and
Oh
we are
yeah,
against it, and that's
yeah,
not true. That's not
sure,
true. There's many things that he said that we agree with, and
sure,
there's it's just that we don't agree that everything he said was gospel, and that's even
right.
mainstream doesn't think that. The mainstream has sort of picked out certain things that they think are just absolutely brilliant, and then a lot of the things he did later in life, they think, well, he was an old man. He can't really take him seriously after in 1916, and that's not true either. But anyway, his basic premise is that Einstein's most important and most valuable work was neither in 1905, which is sometimes called the miracle year, or 1916, which is the year of general relativity, but his most important year was 1911, when he wrote a paper that has since been dismissed. And
Hmm.
he makes a very strong case for why that approach, which was later discarded by Einstein himself, was actually quite valuable. And well, okay, so a little bit of the history is, Einstein's calculations were off. The 1911 calculations were off by a factor of 2, and those were corrected in 1916, and therefore the whole theory behind the 1916 must be right, and the whole theory behind the 1911 paper must be wrong. And that's just unfortunately not the case.
Right.
And he goes on to show that there were several scientists in the 30s. Well, there was Paul Dirac, who kind of supported these ideas. There was a guy named Dick. Why am I forgetting his first name? His last name was Dick. Who basically re-derived the 1911 paper with the correct factor of 2, a slight couple of small changes, but with basically the same approach.
Right.
And there was also Sayama is another one. Why am I forgetting his first name as well? This is from the 50s, who kind of had that same approach to gravitation. I'll get into the details of the approach, but my point is that there were pocketfuls of other people who kind of took similar approaches over the years to Einstein's 1911 approach to gravitation, and that he thinks that there's value in it, and actually expresses a great deal of surprise in the fact that not a lot of people have taken that. I
Hmm.
was encouraged because Dr. Sayama, I think I don't want to say Dennis, but it's anyway, I've read some of his papers and was very excited by them years ago. So to see him being mentioned in Unzicker's book was kind of encouraging to me. And that's kind of how this business goes. Is you hear about somebody, then you kind of forget about it, and then you hear about them again from somebody else, and it's a kind of a chasing all these different avenues.
Sure.
So anyway, basically the 1911 approach was that the there's a, well let's go to Einstein's 1916 field equations, which there's basically in essence what it says is that the curvature, which is expressed in the symbol g, and it's expressed as a tensor, is equal to some constant which has Newton's variable g, which is a totally different variable, times the energy density. So basically, somehow from knowing the energy density, we can know how much things curve. And also that, so how am I going to get? Basically, this constant, which equates those two, is using the constant g over c to the fourth, which I won't. That's c is obviously the speed of light, or known as that. But that equation, that symbol g over c squared, he says, has also been thought of as the mass, or the reciprocal actually, of the mass divided by the radius. So we can think of it as the mass of the universe divided by the radius of the universe in one sense, or it could be thought of as the sum of all the various masses divided by the radius of each individual one. And again, that's a nonsensical idea if you believe that if the universe is infinite. And so that's where you might,
Is that one of the
take
things?
exception.
Is that one of the things that is a sort of assumption that they state right up front, or is that something that
Well,
just comes from the work by the work itself, or was
there
that?
were measurements made in the 1930s by Hubble, and then later, well, he didn't make measurements, but interpreted by people like Paul Dirac and others, who interpreted this as the measurements of the mass of the universe, which was, golly, I'm going to butcher the numbers, but I don't want to take a stab at what those numbers are, except that when you take that number, there's also been physical results based on telescopic evidence that was discovered in the 30s and 40s, which is interpreted to be the radius of the universe. Now, you could say those numbers, I don't interpret them in that way. And I'm not going to say you're wrong. I'm just saying that's how, even today, a lot of people interpret the universe. Some of it's based on, I think, some misassumptions about redshift and about, some other things, which we don't have to get into. But anyway, the bottom line is it was really ironic because that number, c squared over g, turns out to be almost exactly equal, on the same order of magnitude as the mass divided by the radius, if you take those numbers to be interpreted as they were in the 30s. And what he's saying is back in 1911, we had no idea of the discoveries that were going to be made by Hubble, and by his success of 1916, he'd already thrown out the 1911 interpretation, which had maybe that come out in the 30s, he would have gone a different direction. That's kind of his case, and I think it's a pretty persuasive one. That's because Einstein never did believe in an infinite universe. He always believed in a finite universe, and of course that is the paradigm for most of science today. It doesn't make it right. It is one I happen to believe in, and it's an area where you and I disagree.
Sure,
But
sure.
but yeah, pretty much I would say Unzicker's book does not even talk about the possibility of an infinite universe, because then pretty much the whole purpose of that argument would go out the window, because it wouldn't make any sense. And that's so you might take a book like this and say, oh, there's nothing in there that I'd be interested in, because it doesn't
Well, no,
support
no.
an
I think
infinite universe.
the thing is one of the things I was talking to you about to stress to people is that we really have to be. It's not even supportive. It's just trying to understand where people are coming from. If they're going
Right.
to, like if you believe in a finite universe, you have to understand where that's coming from. Okay, you have to suspend some things that you believe to be true, but you say, okay, within this world, within this system they have, what's going on? What are the calculations? What are why do they have that? And try to understand that. And then and not
Sure.
only that, you can actually help people. I know there was one guy who passed away a while back now, who, my gosh, he was a guy that would sit in everybody's papers, and it was in the 2008, 2009 when we first met.
Bob
Um,
Heaston, are you thinking of?
yes, he
Bob
would
Heaston was
sit
awesome.
he
Yeah.
would sit at I don't care if you were talking about turtles made up the universe. He would sit and then do notes, and then you give it to him, and the
Yeah.
guy seemed to have the ability to take and understand in the
Hmm.
context of what the person was doing in their system and then help them with it. So
Yeah.
what you're looking at is a consistency within a system, whether or not you agree with that. So you may
Hmm.
come up and say, okay, well, that you have an ether theory, a finite theory, but this is a problem in your theory, and it
Hmm.
doesn't mean that you're wrong. What it means is it's a problem, and it's helping out. It's something that's very foreign to scientists today, because first of all, there's
Yeah.
this idea that there is one answer for everything, and that's
Well, there is one answer. Well, first of all, like you say, there isn't necessarily there's more than one way to look at things. There's one,
one
and that's
universe.
and that's the value of it. But there's also, not being willing to look at other worldviews is just so limiting. It's
Yeah.
terrible.
Yeah, no, absolutely. So you went through the book and you read this book and you said it got you inspired in a way. What did you? I think it'd be interesting. What did you think was the biggest revelation from his book? What I mean, reading a book. If you were someone you say tell someone if you're hey you should read this book, but what is the biggest sort of takeaway, regardless whether you agree, disagree, whatever? What was that when you read
Yeah,
this?
well, I think the fact that these other scientists, and I should have probably had some of these together, but some of these other scientists have thought about these same problems before and have come up with some pretty convincing arguments. And oh golly, I mean, for me, it is Dennis Sayama. Here's a picture of him, if you're interested. So yeah, that's the guy I
Oh,
was
okay.
thinking of. And also,
He looks like a picture from Scientology.
yeah, it could be. I don't
I'm
know.
kidding. I'm kidding.
But it's fascinating. He's, talked about the where does inertia come from, and what, things like, mass versus inertia, and how do we get those kinds of things. He addressed questions like that. I'm sorry, to answer the question that you're coming up with. I'll try to give you what was the aha experience for me,
Sure.
and it wasn't even in the book, but. If you go back to Einstein's equations, well, there's a couple of different ahas. One is I've been thinking about, the Einstein field equations are given in what's called tensors.
Hmm.
Now, I have to explain what a tensor is first. Everybody understands a scalar field. I like to use temperature as a good example of what a scalar field is. What that means is that for every point in space, there's one value, the temperature.
Hmm. Sure.
And we can kind of get that. Now, if we had, for example, a gradient of temperature, let's say it's hotter over here and warmer over here, then there'd be like arrows pointing from the colder to the hotter, and that would be called a vector field. So at every point in space, there's not one value, but actually three. There's a vector pointing from that direction, and it has a magnitude and a direction. Okay?
Right.
Now, a
Okay.
tensor is kind of like you take the gradient of that vector field. I know that's a little bit weird to think of, but it's like for every vector, there's a set of values that it could be pointing depending on where the vector is pointing. If the vector is pointing this way, then the answer is here. If the vector is pointing this way, then the answer is there. That kind of a thing. So there's a matrix associated with every point in space. That's what a tensor field is.
Hmm. Sure.
And so first I had to explain that. So Einstein's field equations are given in terms of tensors. So there is an energy density tensor out there. And one of the things I've been struggling with, it's hard for me to make this simple, so I just have to explain it. Back in the late 1700s, early 1800s, was one of the world's greatest mathematicians ever, and his name was Lagrange. And one of the things that he came up with in the late 1700s were called Lagrangian equations. And if you've ever studied physics, basically what he did prior to Lagrange, everybody, even Euler and a lot of smart people, did their operating of mechanics in terms of forces. Forces are vectors by definition. And Lagrange said, wait a minute, we don't have to use forces. We can actually use energy, which is a scalar. In other words, we can solve the problems with less information. And that was a fascinating idea. He was able to simplify a lot of problems and use what are called reduced coordinates. And I won't get into all that. But the bottom line is that if you're able, let's say, for example, you have that temperature gradient field and you're able to deduce the temperature from it, then then use just the temperature field instead of the temperature gradient field, which is supposedly 3 times more information. Actually, you can reproduce all that information from just 1/3 of it. My question is, well, gee, can we do the same thing going one step further with the scalar? In other words, can we take this tensor field and reduce it to a scalar field and be able to make sense of that? Or are we going to lose information when we go from 3 to 1, or when we go from 9 to 3 to 1? Mm-hmm. What information do we lose when we do that? I mean, obviously, there's something called integrals. When you take a one-dimensional integral, you have to add a constant to it. So in other words, what an integral is doing is you know the change in things, but you don't know the thing. So the value itself makes no difference because you're only interested in the changes in the value, right?
Right.
That's why when you integrate something, you add a constant. So it's the same kind of thing when you're going from a scalar field to a vector field. You're looking at the changes, generally a gradient or something like that. Mm-hmm. So so what I'm saying is you could add a constant to all that. So that information is not really all that useful, the constant. But what else are you losing? And so I've been struggling with those questions. His book kind of inspired me to do that. That's one of the inspirations for me, is just delving into that. I really want to get a good answer. And maybe there are people who've already addressed these questions and it's like 100 years ago, but I'm still struggling with that whole concept. Where in my background, just so you know, as a double E, I studied information theory, and I'm real interested in what information actually is lost if there's 3 times as much information in a vector field. I hope that's not too boring for some people, but that's the kind of thing.
All right, they're gonna, we get to, some people are asking for more information like this. A lot of times they talk about in generalities.
Yeah.
But so.
Well, I'll give you my second takeaway.
Sure,
is completely
absolutely
different.
Okay.
And that was this was a really aha thing. Now, I believe in a universe which is finite, but unbounded. What that means is that there's no edge. It's not like a 3-dimensional universe and then you come to a 2-dimensional surface. You never bump into the end.
Sure,
I don't believe that occurs. What I believe is that our 3-dimensional universe is wraps around itself. And that's not that hard to understand. I like to use the surface of a globe as an analogy. The surface of a globe is a 2-dimensional space which is bound on top of a 3-dimensional sphere.
Right.
And so if you can imagine, that's not that hard to imagine. You don't come to the end of the earth like people used to think, supposedly in Columbus's day, people would worry about coming to the end of the earth. Well, there was no end because it's round. And the same thing with the universe. I believe the universe, there's no end. It's just if you travel in one direction long enough, you eventually come back the same way you would come back, if you traveled around the earth. If you just go in one direction long enough, sooner or later you come back where you started. I don't think that's real complicated. Okay, Einstein's relativity is generally interpreted by most people to mean that the space itself is actually curved. In my view, the space is not affected by it. In other words, the only thing that's affected, it's telling us the path of light. And I have to take another tangent. I'm sorry for doing this, but in the 1600s, there was a guy named Pierre Fermat. Fermat came up with the principle of least time. And least time was, even before him was a guy named Snell, Wilhelm Snell, I think it was, who came up with the idea that, if a light beam would pass through one medium and then through a denser medium, it would do it at a different angle. And it's not that hard to understand. If you think of the analogy of rescuing somebody in the water, you're standing on the ground and you want to rescue this person that's, over to the side here in the water. Well, you could go, you can obviously travel faster in the air than you can travel in the water. That's the point. Right. And so one way to go would be just to go straight through, and when you get to the distance, in the water that he is, and you turn and you go right. Well, then you would maximize the amount of time that you spend on land, but you still wouldn't do it in the least time. Because you'd be wasting, kind of going the wrong direction. Or you could go straight to the guy, but then you'd be spending, proportionally more time in the water than you should. So there's some in between where I hope this makes sense, where you kind of, there's a certain angle where you'd go on land and then a little sharper angle through the water. And that's that's the path of least time, and that is the path that light would go. And that was discovered back in 1600. So basically, as I understand general relativity, one way to explain it is remember I mentioned that there's this idea of energy density, where it's more dense. And again, I know Edward Dowdy's going to argue with this, but let's just take this as a premise. When there's a massive object, the light is bent around this massive object. Okay, and it may be because there's stuff around there and not necessarily because of the math. I don't want to argue with that right now. Let's just accept that premise. The point is, what Einstein says is like, okay, well, I know that light travels the path of least time, same as it did, for centuries before Einstein. What I want to do is, rather than try to find out what that path is in my space, I want to sort of bend space around, excuse me, so that my path is a straight line. And that's basically what he did in general relativity. He's, instead of having this weird, path that kind of goes all over the place, I just want to have my, if I can think of a Picasso painting, where everything's distorted, I kind of distort everything on purpose so that my path ends up being a straight line. And I think that's a brilliant idea myself. Why wouldn't we want to do that? The problem is people are then taking that and saying that space is actually bent. And I don't think, that's where I take exception. Oh, space has not changed. Space is just space. It's not doing anything. But we're kind of taking this approach to it, and that's perfectly fine. That's my view. And so I hope that makes some sense. So here's my revelation: was looking at Einstein's equations, kind of for the first time. I said, okay. If the universe is what I say, it's like a three-dimensional sphere, if you will, around a 4 space, then there is naturally going to be a curvature. I mean, I can't get rid of it. It's, just like there's curvature on the globe. I can't get rid of it. And so then I said, well, wait a minute. Einstein's equation has curvature in it. And so then I say, well, how much energy is in the universe? How can I know? Well, gee, if I were to just apply that equation, let's just say so the universe has a certain size and therefore it has a certain curvature, and I can plug that into Einstein's equations, and then I multiply it by this or divide by this constant, I get an energy density. That's going to tell me, if I know the volume of the universe, that's going to tell me what the energy of the universe is, how much there is. And it turns out that is exactly the number that we got experimentally back in the 30s and 40s. That's the aha moment for me. Wow. It's like, that's really amazing. Einstein's equations is actually making a prediction. And there were other people who were saying this, empirically, that this was the case. And there was lots of really good examples of it. Oh, I remember Einstein's equations in a different set of equations had a 1 plus GM over RC squared. That's a term that's commonly found in electrodynamics. And he said, okay, I can explain the GM over RC squared, but what about the 1? This was Professor Dick that made this observation. He said the 1 comes from if we plug in the mass of the universe divided by the radius of the, put those numbers into that expression, we get exactly 1, because by definition, GM over RC squared is 1. That's, in other words, RC squared equals GM is what he's saying. And it's like, wow, that was a real breakthrough. I hadn't thought of it in that way before. So that was something that, again, Professor Unzicker didn't come up with that. That was Professor Dick back in the 50s, I think, that came up with that. But that one just floored me. I was like, wow, it was worth reading the book just to get that one. So I hope that wasn't too technical.
No, that's okay. It's what you're talking about. Like I said, people are not getting a lot of technical information sometimes from my videos. So it's good to get into the nitty gritty to either scare them away or.
Sorry. These are the kinds of things I lie awake at night thinking about.
Absolutely. No, what I think one of the interesting things I see in it is that I think one of the questions you say that the universe is a finite and you can sort of measure it and that kind of thing. Now, when I look at it, if you are trying to, let's say, do a whole system that is all the particles, if you're not believing in an infinite universe where it's all over the place and
right.
you're basically saying, I want to get all the basically movement or energy in the universe accounted for. And so I can see that's it is a different approach
Sure.
but I can also see it's somewhat valid, because what you're sort of starting up as a top down. Now, so the way I look at it mathematically is that if you start with that, then everything has to sort of agree with it. All those things have to sort of make sense, all the equations that you're using, all the
Sure.
math.
Well, there's tons of little ahas that I've gotten along the way. Lots of confirmations, but I
So
won't
my
bore you with
question
all of them.
my question to you is this question we always talk about is, it's a vocabulary for sure. I'm going to have a yawn here because it's so exciting to me. I repressed it,
That's
but
okay.
no. But the question, one of the things is we talk about is space time, and we
Hmm.
do talk about math. And you're always talking about the two terms. I can't remember the two terms you're talking about, where you have the universe and then the actual math systems that you use for them. You had these
Hmm.
long words. What were
Uh,
your?
I think a couple of weeks ago we talked
Yes,
about the Platonic
yes. There you go.
ideal worldview and the Aristotelian experimental worldview.
Right,
You
right,
know, and
right,
there's the world of reality, the world of actual things, and then there's the world of mathematical descriptions of those things.
right.
And the link between those two is not as obvious as I would say the vast majority of scientists would like us to believe.
Yeah, that's very very true, and I think that's where we get into trouble. So the way you put it
Yeah.
is very very
The other thing,
interesting.
and I make this criticism of not necessarily of Einstein so much, but more of Einstein's followers, and that is if you look at Einstein's special relativity, that's the 1905 stuff. He talks about he makes basically two assumptions. One is that the speed of light is the same in all reference frames, and then the second is that all reference frames, the reference frame we're looking at are inertial. The laws of physics are the same in all inertial reference frames. Well, the problem I have with that is basically what we're doing is we're trying to define physics in terms of light because he uses light in his assumption. You follow what I'm saying? He's
Yes,
assuming that he knows what light is
yeah,
when he talks about light being the same in all reference frames. Well, what if we don't agree about what light is? Then we kind of have to reinterpret that. So in my view, light is not a something to do with space itself. It has to do with the particles, just like all the other constants do. The Planck's constant, the electric charge constant, the Boltzmann's constant, the interaction between particles. Why is light, the C, why is that a constant that has to do with space when nothing else does? I
hmm
don't, I don't, I don't accept that. And so so yeah, in one sense, he's right because I believe this, what it was called the speed of light. I believe it's the speed of charge. It's the speed with which things inside a particular atom are circulating relative to the other things in that atom. I believe that's what it is. And yeah, it's going to be the same no matter how you look at it. That's true. And that's just a totally different take on 1905. And there you go. So, and another thing, like I said before, people are always wanting to bend space, and they do it so much that they forget that that's just an exercise to get them to actually understand the problem better, instead of they think it actually is occurring. And then they
yeah.
get wormholes and all sorts of bizarre things, which I don't agree, I don't accept. you
hmm
know.
Yeah, and one of the things is we get constantly is the idea that okay, space, space time and tensor equations. I had a friend read my book, my father and I's book on particle the particle model, and we have a pushing type of gravity. We have a light model for light. Everything's in physical terms, everything, and
Mhm.
the guy. Handed it back, and besides not being able to get the idea that just a model where you have gravity as a pushing thing. He's saying, well, what do you believe? He says, well, I believe, the tensor equations that describe space-time. And I said, well, that's good. It's a mathematical system, but it's not a reality of what's there. And he
Mhm.
says, no, it is. Uh,
Yeah,
he said
yeah.
he really got this argument where I realized I just backed out of it because I knew
You're not
we're gonna win
get
it.
through to
But
a
he
guy like
basically
that.
said, he said no, tensor equations are real, they're physical. And
Yeah.
at that point, what we've done is we've fallen in love with our math. That's what we've
Yeah.
done.
And it's really sad because they're wonderful tools, but we have to
Yeah,
understand what their limits are. And so I'm not dissing Einstein's ideas at all. I think they're great, but we have to figure out, what did he actually mean, and how do we interpret it? And there's more than one way to interpret all of those equations, and that's the problem. Is People get married to their interpretations, and they
Yeah,
really think it's reality.
the other problem is, and you had mentioned it, is I think similar to what we've talked about and I've talked about, and that is, we have all these experiments, we have all these that they say show Einstein's general relativity correct or special relativity correct or incorrect, well, correct mostly. And the problem is it's really hard to say anything about it when they don't have a model for gravity. And what I call model, I'm not talking about math. They don't have an idea where you can, okay, just describe the physicality of what that is to me. And if they can't do that, then it's really hard for us to say, well, how is your detector really detecting gravity waves if you have no physicality of what gravity is? And it's really, really hard to even. That's why people say, well, what's wrong with the experiment? I said, well, it's not what's wrong with the experiment or the detector. It's wrong. What's what they don't know, and it gets to be sort of lost to me. It's
Hmm.
basically for instance, the LIGO gravity wave detector is basically very similar to the Michelson-Morley, right? It's
Hmm.
basically splitting a beam and having it come back around, and then okay, there's interference, and because of the interferences in a certain way, then of course, we have to imagine then that's okay, that's caused by this. I mean, there's so many assumptions upon assumption upon assumption, and without a model at the bottom. So when you say, okay, well, just give me in description of the physicality of what light is, what are the physicality of what gravity is,
Hmm.
and then it gets to be a game where they say, well, what we see, what they live in their interpretation, they're convinced of it, and I have people talk about when I say that, I said, look, you can interpret it any way you want when you don't have any idea what light is, you
Hmm.
know, and that's one of the things I think that people fall into, and then therefore you also get in a hard position where people are saying, okay, Dave, well, here's their model, explain to me where it goes wrong. I can't see any logical flaws, and I say I can't see any substance to it yet. So, I mean, yeah, are they detecting something? Maybe. Even Unzicker put on I don't know if you saw, he put some graphics
Right.
that they show out there on Facebook, and he said, "Where's the signal?"
Mm.
Because then you have on top of all of this madness, and madness in the sense of you trying to grab a hold of something. It's not that
Right.
I can understand the consistency within what they're saying. I can read it. I can read articles. I can see why. Oh, this is how, and this is why we interpret it. But the moment then you go say, okay, what is the signal you're really getting? Can you show me the
Yeah.
raw data? Oh, then all of a sudden and so it's sort of like politics is in this country where you have things being made up, like the Russian scare is being made up, and everybody then talks about all the details, and then all of a sudden, when you say, wait a minute, show me the proof for that the Russian scare before you even get to what the
Right.
consequence of it is. It's the same way here. Show me,
Yeah. They're jumping 10 miles, 10 steps ahead. They haven't done step one yet. Yeah.
and
That's our problem.
and that's a problem. So what you end up is that say, okay, well, you can't really disprove it, so we're not even going to listen to you. When in reality, we can't even begin to start with it because we can't, we can't even trust the data that they say that they're marking because we need to see it. It's like the Higgs boson where they had two teams find it. They're going to
Yeah.
find it. They were going
Well,
to
sure.
find it.
You
It
torture
doesn't.
the data long enough, it'll confess to anything. Like that one.
I like that. Who said that?
I got that from Chuck Missler, I think.
Yeah. But anyways, I think that's part of it, and I think one of the things I want to stress for people listening to Greg, and maybe you don't agree with finite, or maybe you don't agree with infinite universe, but the thing is, you have to understand that you have to understand your own limitations to what you're talking about. You have to
Mhm.
understand the separation, which you are clearly stating over and over, and that is, there's the real universe, which my dad says it doesn't care about math. The
Right.
universe does
Exactly.
not
But it
care.
works. It works perfectly,
Yeah, it works fine, and even though some of the designs of we humans, I think I could have improved upon, but no,
That's a different
yeah,
story.
yeah,
Yeah.
I'm just kidding. But regardless, I think it's you you really just have to be careful about understanding the words you're using, understanding the math you're using, understanding the assumptions behind those. so that you have a good handle upon what you're talking about.
Yeah, well,
And
and it's also it's definitely true, and this is just as a matter of principle. People who are dissidents like you and me are forced. Really, we need to know more, not just
yes,
as much as conventional scientists. We need to
absolutely.
know more than conventional scientists do because we need to understand conventional science. And I think for the most part I do. I'm not an expert on everything, but I mean, I know things I know pretty well, and that's also. But I also know a lot of things that conventional scientists don't know. And so that's just, I'm forced to be there. I have no
To
choice.
understand, to criticize and to understand what's going on in the world of physics, you have to basically say to yourself and understand that we have to understand a a person and their theory much more than that person. That is, if
Yeah.
you're going to find a problem with Einstein's theory of relativity, you really have to understand it actually more than perhaps Einstein himself, because how that's how you discover something that's wrong with it, right?
Exactly. And I'm just as a one of the things that really has caused me to believe in a finite but unbounded universe is precisely this issue: is the idea of does curvature exist, and if there is curvature in some way connected to gravity, and if there is actual physical curvature, that there must be some way to express that, and that's why this was so really such a hot button for me,
Mm-hmm.
with making that connection that this really, in a sense, is already contained in the equations. It's like, wow, that I never thought of it quite that
Now,
way before.
when you talk, and one of the questions I would have for you, maybe my listeners too, okay, you're not talking about the physicality of it, but you were mentioning, it seems to me, and maybe I'm misinterpreting this in my world, but you are saying that you're trying to find out what's sort of a description. You're looking at the mathematical parts of it, which then
Right.
inspire you, and then you say, well, in reality, it's going to have to translate into something physical. So
Sure.
my question
Well,
was, what is
let me
what is the physicality of what you're talking about in this
okay.
curvature? How's that
Yeah,
working?
I'll give it to you. This was an insight I had probably, I don't know, 3 4 years ago, and I thought it was pretty cool. See what you think.
I
And
think it's
basically,
terrible. No, I have no idea. I
basically,
haven't
it's
heard
this,
it yet.
there's something called Gauss's law. Gauss's law
Right,
says
right.
that if you have a volume, the surface area, if you know the field coming out of that surface area, then you can know what matter is inside of there. So, for example, if the matter happens to be charge, then if you have the electric field coming out of a surface area, you know how much charge is in there, which is pretty interesting.
Sure.
It's like doing an integral. When you do an integral, if you know the endpoints and you know the function, you don't need to know all the points in between. You just know that you know the values, and
Hmm.
which is that's the way integration works. Well, it's the same kind of thing. If you know the stuff going on at the boundaries, then you know everything about what's going on in the beginning. A guy named Carl Gauss discovered that in the 1830s, and so what's fascinating about that to me is that the proton, let's suppose I have a real simple hydrogen atom. I have a proton inside and I have an electron, that's kind of outside. If I put my little Gaussian sphere around them, it's going to be zero charge. And yet it's not quite zero. This is one of the things that Dr. Lucas showed, and I've been working on this. He wrote this paper back in 2008. And I think it's brilliant myself. Basically, he's showing that due to the structure of the atom itself, the fact that there's the positive nucleus and there's this negatively charged outer shell. It's not quite that simple. It actually has to do with the dynamics of things moving within it, but I won't go into that. Bottom line is that there is a net force between two. In other words, I got two atoms. I got the positive to positive is repelling. I got the negative to negative repelling. I got the positive to negative attracting, and the positive to negative attracting. So I've got two attractions and two repulsions. You'd think that the net force between them would be exactly zero. And he shows that it's not quite zero. It's a little bit attractive. And he says that's what gravity is. And I agree with that. So then I'm thinking, yeah, okay, I believe that. And yet, how can I get that? Knowing Gauss's law, knowing that the positive and the negative, if I were to put a cloud around it, I get zero. How do I not get zero? You know? And so here's the insight that I had. See if this makes any sense to you at all. But if you can kind of imagine an Earth, now I'm just going to a two-dimensional analogy here to give you a three-dimensional idea. Okay, so the two-dimensional analogy is that my proton is sitting at the North Pole, and my electron is circulating. I think of it as a ring of charge, maybe at 89 degrees, or it's circulating around it. Okay, so when I say what is the distance between the positive and the negative and some other particle which is maybe located at the equator, then because of the curvature, just because of the curvature, it's no longer zero, because there is now a difference between the one that's sitting at the North Pole and the one that's slightly below it. I'm not going to get zero anymore. Are you following me?
Yes, I am.
And it's because of the curvature. It's the curvature that causes that difference. And that's what has been bothering me since 2008. What is it about I agree with Dr. Lucas that, yeah, somehow I'm going to get gravity, between these two particles, but I can't, Gauss's law doesn't allow it. Only way I can figure out how to get it is to have curvature. So that way, the thing that's inside is going to be slightly further than the thing that's outside. And so I can get a slight attraction between two particles by virtue of curvature. Well, how much curvature do I need? I need enough curvature. That's the curvature of the universe. And that's really foundationally why I believe that there is such a thing as a finite universe. Einstein's equations kind of support that. A lot of things have actually supported that. Some of these measurements that were made in the 30s support that. And I don't agree with a lot of the things that happened in terms of the way things were interpreted astronomically by Hubble and so on. We don't need to go into that.
Right. That's a different story.
Nonetheless, there is quite a bit of evidence to show that there have been measurements made of mass and radius and things like that. And that's where I'm coming from. I'm coming from how on earth can there even be, an attraction between things? So in other words, Lucas is not wrong. It's just he's not complete. There's more to the puzzle than that.
Okay, my question is, though, to you. I understand what you're saying, but within your system,
Mm-hmm.
there seems there would have to be some direction, or there isn't direction.
Well, I don't
To the
think of it as a
curvature.
push or a pull. I know that's kind of how
No.
said.
That's not
I
what
just think of it as, is there an attraction? Well, let me back up one step. Most people think of like, for example, I've always said this thousands of times. There's no such thing as positive and negative charge. There's only attractive forces and repelling forces. When things are circulating, what we call positive, I believe, is left-handed circulation. In other words, things are circulating kind of like a slinky that way. And then, what we call negative is right-handed circulation. I forget if it's the other way around. But bottom line is, if you get two circulations that are opposite, they look like mirror images of each other. They're going to have more in common with each other than opposed. I hope that makes sense.
Mm-hmm.
When they're mirror image, when you look at something in the mirror, you have more, like your right side is on the same as the other guy's left side, right?
Mm-hmm.
And so mirror images are going to have more in common. I hope that's obvious.
Mm-hmm.
And therefore they're going to repel more. So that's why they're going to attract more, because what makes attraction is currents that are flowing, simultaneously. Whereas if they're floating in opposite directions, they're going to repel. You're going to get more of that when you have them being the same. So like-minded things are, right-handed and right-handed are going to have more opposites when they're put next to each other, because they're not mirror images of each other. And now I sometimes forget where I'm going with all this. But my point is that there is no such thing as charge. There's only the force between what we call right-handed and left-handed things. Same thing with gravity. There is no such thing as gravity per se. There's only the force between objects, like Lucas has it. We're going to see the force between them, which is slightly attractive. And so that's what is that? How much is that force in comparison to other force? That's gravity. That's what it is, in my view. Mm-hmm. So I don't think of it in terms of being a push or a pull. I just think it's an attractive force.
I understand that. I wasn't saying push or pull, but I also did a little spiel on charge. Charge is, my father and I looked at with Lionel Deneu's underwater experiments, where you see that flows together attract, and flows that hit opposite and repel. And
which is consistent with Ampere's law and Bernoulli principle and all those things.
Right. So that is something that I think is in common with what a lot of people in actually the dissident world and or mainstream. How do you see that? Is this more a dissident type of point of view, or do you see mainstream also sort of looking at this?
Looking at what? Looking at,
Uh,
well, let's put it this way. The mainstream does not look at models of the electron in the same way that I do. Like people like
right.
Dr. Lucas and Common Sense Science, we regard, electrons as structures of flowing matter. So I don't want to be so simplistic and say that it's a ring, because it's not exactly what it is. But
Right.
ultimately, all flows can be broken into. I wrote a paper on this one time, if you recall.
Right.
Whereas any closed path, any path that ultimately comes back into itself, can be broken down into a series of ellipses, just like a Fourier series. So you can have a first harmonic and a second harmonic, and so on. So to reduce it, to a linear combination or whatever, a combination of a bunch of paths which are ultimately circular or elliptical, is not being idealistic. That can be done. So to look at simple right-handed and left-handed circuits that's how I view matter. In some way, all this stuff that's we call the electron is held together by its own internal motions, which is circulations inside it. This is not how mainstream science looks at things. They see an electron, and they say there's a bunch of properties that the electron has, and we just have to accept all these properties on faith. And if we delve into what that structure actually is, then we'll be violating Heisenberg's uncertainty principle, and we never want to do that. So they just leave it alone. That's why I say there's no competition, because most people aren't even looking.
Sure. They keep going down further and further, which is amazing.
Well, yeah, they're looking to try to smash trucks together and see if they can get littler trucks, but they're not looking at circulation as part of the structure.
Well, they're not. I mean, they're not even to make it even simpler. They're not looking at the structure at all.
No. Well, and it's because, it goes back to people like Niels Bohr. Niels Bohr was famous for saying, if you think you understand quantum mechanics, then you must be, you obviously, you're not. I don't remember what he said exactly. But I mean, he forwarded the idea that if anybody actually thinks they understand it, they must be insane, because implying that the laws of physics are different when you get down to the level of electrons and protons and stuff than they are on the real level. I don't believe that. I believe that the laws of physics are the same for electrons and protons and particles as they are, that we experience in the real world. We just really haven't understood them yet. And so you can call me crazy for believing that, but I believe the laws of physics are the same everywhere.
It's sort of. It's really ironic, because if you look at what at least the interpretation of what Einstein said, and that is all physics is the same in all
he
reference
believed that.
frames. But that's a wholly different story, because what it means is to believe the way it's described, physics ends up being different in each place, because your clock is slowing down, your length. So it gets to be pretty.
I could accept. I could even accept, there's a clock difference. That's not quite the same as saying, the laws of physics and the reality of physics is different at the quantum level. And that's,
sure.
I don't know. That's not quite that's even more harsh than saying time is, altered. And I'm not supporting that idea, but.
No, I agree with you. And I believe that too. My father and I believe the exact same thing, that the physics is going to be the same up and down. Now, the question I also have for you, and again, because it's not in a realm or a model that we're accustomed to, my father and I. Now, when we're going to be wrapping up here soon, but one of the questions I have is, with a finite universe, is it infinite down, or is there going to be a level where you stop if you can't go up further?
Yeah, I believe in infinite down, because if you were to, in the sense that you're saying, infinite down in the sense that you find a structure, and you don't come to an ultimate structure that has properties but but you can't break it down further. Everything can be broken down into something which can be broken down into something which can be broken down into something, which ultimately means a continuum. That's what a continuum is.
But do you believe that goes up as well?
Well, it does, in a sense that you can never come to an end. Remember, you can't come to the end of the universe, right? But nonetheless, it's finite.
Right.
So, you can't come to the end of a globe. So it's finite it's finite, and yet it's infinite in the sense that you don't come to the end. I saw there's
But
maybe
is there
two.
a structure above that that's doing the same, that is part that this is a
Well,
part of?
that brings up a whole another set of questions, and maybe this isn't where you wanted to go. But one of the big questions I've always had is relative to what? How do we know that something is moving? If the universe is finite, what's outside of the universe? Is
Right.
there, in other words, if I can't describe a three-dimensional universe without a four-dimensional globe, does that mean the four-dimensional globe exists? I don't
Right.
believe it does. I don't.
Right.
But I cannot describe, just in the same way I can't describe the surface of a two-dimensional globe without the three dimensions of the globe itself,
Mhm.
the inside. But that doesn't necessarily mean my space has to have that inside in it, if that makes
Mhm.
sense. I don't know if that answered your question. Probably not.
Probably
Sometimes I
not.
go
No,
off and
no, no. That's okay. That's okay because some of the times those answers are, I mean, some of the questions are not in the realm of
my
what
problem
we
is
can
I get
ask.
thinking and I forget what I'm talking about. Sorry
So,
about that.
so, so it sounds like
That's my egghead habit.
no, that's okay. It sounds like that you and Unzicker have actually quite a lot in common. You said you'd like to talk with him because I'm
I would,
sure
yeah. I
he's
had a
gonna
few things I'd
watch
like to bring up with him.
this.
I've got a paper. I've got about 10 pages into it, and I
Maybe he'll
won't bore you with all of
co-author
that.
with
But
you. Maybe he'll
I kind
co-author it
of
with
some of
you.
the things I talk about is well, I'll just say it this way. One of the things that really interests me is the ratio, which would be the gravitational constant g times the mass squared. I call that a strength because um, it's this. If you can kind of think of Newton's equations, which is m1 times m2 over r squared. I hope that you know that equation. Basically, what we're saying is that a force is equal to a product of some stuff times a constant over an area, or the radius squared, or 2 pi r. So what that means in effect is as the radius is increased, the force is decreased in proportion. That makes sense?
Yes,
Okay,
yes.
so the product of the force times the area is constant. So force times area is what I call strength. So gm squared is a strength, and ke squared, Coulomb's constant, times the electric charge constant are also another strength. The ratio of those strengths is on the order of 10 to the 40th. Why is it that number? It was Paul Dirac who was the first to notice that, hey, that's kind of the same as the radius of the proton to the radius of the universe based on the measurements we've made. That can't be a coincidence. And I agree with him. That just can't be a coincidence. And it turns out, I like to think in terms of energy instead of mass, but that's a whole other thing. Anyway, so one of the things that's really interesting to me is those ratios. Another one of those ratios is the Ke squared over Hc, which is the fine structure constant. It's 1 over 137. And people have been trying to figure this out for over 100 years. And I believe I have some answers on that. In fact, still working on an integral that's a tough one that may give us an actual answer and an actual reason for believing it has the value that it has. So we'll see. But those are some of the most important numbers in physics because they're just plain old numbers like the number pi, y 3.1415926. I think it is. That's as far as I know it.
There you go.
But the point is, it's a number that exists, and there are a bunch of numbers like that in physics, and we really don't, in the same way that we can describe, this is sort of maybe a good place to end, the same way that we can describe that number as being the ratio of any circle, the circumference to the diameter. No matter what circle you pick, that's the ratio of those two is always going to be that special number pi, right? Okay, can we do that with these other numbers in physics? And I believe we can. And so, for example, I'll just quickly give you my definition, I think, of the fine structure constant. Actually, twice the fine structure constant, well, over 2 pi, but we won't worry about the detail. I believe it is actually the difference between the electric and magnetic energy of a circuit, over the sum of the same thing. That's what it is. And I'm this close to actually having shown that. This was basically what David Bergman was showing over 10 years ago. And so it's not a totally new idea. But what I'm excited about is I gave you in words a meaning for that number. Then if I can show that it actually is that number, I think I will have shown something new about physics. And that's what I'm hoping maybe to do with this number, which is the ratio of those two strengths, the gravitational to the electric strength, 10 to the 40th, 10 to the minus 40th. Why is it that number? It can't be arbitrary. It's got to mean something.
Well, sure, sure. I mean, even the number system we use, like Peter Erickson shows us all the time. it's a particular number system. And if we have different types of number systems, we're going to have, but the actual physics of what those things are, the mathematics system can change, but the ratios and what they mean are going to still end up being the same. It's just going to be
Mhm.
a different take on it. Well, I tell you, I mean, I think what you guys should do is get together with Dr. Unzicker and
Yeah, I'd love
really
to do
get
that.
talking. I think you guys would really hit it off. And the question is, will he really want to get that close to us? Because
Oh
we're
no,
sort of, well, no, it's not that,
we're a
not
little too
personally, but
wacky for him, huh? I
well,
suppose.
you know, because I don't know if that's going to hurt his access to, you know, the people in the
By talking
mainstream.
to me, some other people might say, "We're not talking to you anymore."
Well, no, no, it's
Who
yeah.
knows?
Well, I don't know. You know, some people they have to be careful on their association with a bunch of dissidents who are
Yeah, who knows?
associated.
Well,
But I'm
I don't
not.
even.
But I think even you know, I think it would be, as he says, he made it very clear. One of the things he said, which I repeat a lot now, is he says, "Look, we're pretty much on our own when we're working."
Yeah.
We're not going to have even necessarily the people around us agreeing with it, not even the
Hmm.
supporters in our own group, which are open to the
Not even
idea of,
other dissidents. It's
yeah,
just the
exactly.
reality.
And
Almost everything I've come up with has been all totally on my own.
yeah, and
I
he
don't
says
have
that
people just hold my hand, telling me what to do. It just it doesn't work that way.
you don't go to the Greg Volk Think Alike Club out
No, I
there.
don't.
Yeah,
Hopefully, I can convince a few people that I have some decent ideas, but yeah, for the most
yeah.
part,
Well, I think that's you know that's what he says. You just got to work on it, and I'm sure him working on and one of the things what we try to do in the CMPS, right, is to try to get people with like ideas to work together and bounce off ideas of each other. So, who
yeah.
knows? Maybe you could start your own channel and talk with them.
Yeah, you've mentioned this in the past.
Then you can go off. Look, I enjoyed Dave, but we ended up in a place. Well, I mean, one thing we do agree, it's turtles at least all the way down,
Oh
right?
yeah,
There we
absolutely.
go. I mean, so at least the turtles, well, half of infinity, well, I guess half of the
Close
turtles.
enough.
Yeah, I don't know. Yeah, who knows? But it's always
I think you go to
fascinating.
twice infinity, maybe. Yeah,
It's
whatever.
always fascinating. And of course, what you needed to do, obviously, with your small collection is to have one more book in your collection and in your head. That's one thing you really need, like a hole in your head, because you have so many. But it's always a delight talking with you because you are absolutely so knowledgeable about physics outside the mainstream and in the mainstream. Like you said, we have to understand that I mean, like I look at Karazani. Karazani understands the derivation, for instance, of the idea that you can derive the Lorentz equations from special relativity without the need of ether, for instance.
Hmm.
That was understood up and down by Dr. Karazani. I mean, if you look at the math and that, you have to just say this guy looked at it. And the only way to do that is to look at it closer than the people who actually wrote it. So when you
Yep.
look at that, you find out that no, there's a 3/2, uh, 3/2 instead of a 1/2. That is, instead of the square root, you have a 3/2 root of the number if you follow what they're trying to do. So when they say they do that, and then you actually then try to do the math for it, you find out that it's wrong. So often, you
Mhm.
know, it's not often, it's the reason science advances is because the people who look at what's currently been talked about either missed something or that they made a mistake or actually some of the work, like in this case, I guess is a good way to end this, is that in the book that, why don't you hold that book up again? What's the title of that book? The Einstein's
Yeah, this
Lost
is
Key.
yeah.
And you're saying basically you're saying, and what Unzicker is saying is basically Einstein had this great idea that never sort of got the light of day, and
Yep.
people, or at least he said, and so it just blew over. So those are the ways we really advance science. So it's not really important who's right. It's more important for us to look at it, and it's certainly really hard for the mainstream to accept that. Well, for us to make criticisms of Einstein or the Big Bang or redshift or whatever it is, that we actually have to know more than them, that just doesn't go well with them. So,
Well, sorry,
yeah,
I showed you one of the times we met a few weeks ago. I showed you that one of the people that the version of Einstein's translations in English that I use was by Al Kracklauer, who's a member of the
yep,
NPA.
yep,
So, go figure it. It shocks me. Well, just like that stuff by Ampere, there's a lot
yep.
of really important papers that are just completely being neglected by what we might think of as conventional science. Yet they got to read their journal. They got to be up on what happened last week, but they're not reading the stuff that was written 100 or 200 years ago.
Well, yeah, it's like the
I
neutrino.
like to
Yeah,
read that stuff.
yeah. Well, it's like the neutrino when you ask the people and you question its origin and say, look, the origin comes from special relativity being applied to decay cases, as Quarzani, at least in my opinion, clearly shows. They go, well, no, well, the history, we didn't know much back then. That's what they say. And they
Yeah,
just
it's
throw
crazy.
away the entire thing where it comes from. It then takes a life of its own. It then cuts its origin and says, okay, no more. That doesn't make sense. That's not where it comes from. And then they end up saying, well, well, of course it exists, because if it didn't exist, these equations wouldn't work, which is a circular problem,
Yeah.
because their equations work because it's built around special relativity, which has the extra energy, and so of course, and then it's just like, oh my God.
Hey, this is maybe a thought to sort of just piggyback on what good way to end. There's a guy named Morton Adler who was. I have something called the Great Book Series. It's a 54 volume set of what somebody considers to be the best books ever written. So it's got
Hmm.
Shakespeare and it's got Plato and Aristotle and it's got Newton. It's got some science ones in there. So
Right.
Newton and Faraday are in there.
Hmm.
And my point in saying this is that one of the points Morton Adler makes, who's the editor of this series, is that he calls it the great conversation. And in a way, it's like, these great minds are all speaking to each other. And
Yes.
many a times they're hundreds of years apart.
Yes.
And so I like to, I don't consider myself the world's greatest philosopher, but I've spent a fair amount of time reading some of those works, works by Kant and also works by people like Huygens and Newton and stuff like that. I mean, I've read those books, and I do feel that when I read a book, I mentioned this earlier, by like this one by Unzicker, I interact with it. I don't feel like I'm just reading it passively. I'm actually, it's making my mind go in certain directions. And that is in many ways more valuable than the stuff I'm actually reading. I hope that makes sense, but
No, it
that's
makes sense
how I think of
perfectly.
as a great conversation it ought to be.
No, it is, and that's absolutely true. When you read something, you feel akin. You wish you could just get them right next to you and talk with them.
Yeah,
And I
yeah.
think,
But in many ways, it's better,
yeah,
because you can
yeah,
kind of interact with it. That's
yeah,
how I would read all my books, is
yeah.
that way.
Yeah, and I think that's what happens. I think even amongst us dissidents, I love to get books really out there and take a look at them and see what that stimulates my brain. But I really do think there's a commonality about people who have changed science. They all seem to be the same kinds of thinkers, the same kind of
They're
critical
all
thinker.
outside the box thinkers, yeah.
Yeah, well, I think they also look a lot at the history. That was one of the first things I
Hmm.
did. The first thing I did as a dissident critical thinker when I met Karzani was to go to the public library in Long Beach, California, where I lived,
Hmm.
checked every book out on the paradigm shifts of science. I wanted to know, here's a guy who's looking to who's saying that we need a paradigm shift. Things are wrong with mainstream, and I just said, well, what happens? And I read something like amazing that's found that Newton spent the rest of his life retired, being I guess the head of the mint where they print money because there's a lot of physics in that involved,
Yeah.
and spent the rest of his life arguing his ideas with his peers.
Yeah.
Meaning he
Well, he
was
spent a lot of
defending.
time
He
just
spent
working on prophecy and not even math at all, but
Yeah,
yeah.
but he also spent a lot of time having to defend himself. People don't we always look back and think that this
Yeah.
was just such a wonderful, everyone, oh no, Newton, he was like totally accepted. What are you talking about, Dave? Whoa, wait a minute. We accept him now, but if we probably went back, we would probably be very shocked. So
Hmm.
I think it's, I think a kinship is what we feel,
Yeah.
and that's what you
Well,
feel.
look at Avogadro. I mean, Avogadro's ideas weren't even accepted in his own lifetime. It wasn't
Yeah.
until 50 years after that somebody said, "Hey, remember this Avogadro guy?
Yeah.
I think he had something there."
Yeah.
And
Yeah.
so then his ideas were accepted. Once they were having trouble figuring out how to, calculate masses, it just didn't add up anymore. Well, maybe there's
Right.
more than one, atom per, or one mass per atom or whatever.
Yeah.
So
Anyways, thank you so much, Greg. I appreciate it, and I guess we can continue to do this. There's always things to talk about.
absolutely.
I'm certainly, hopefully, a lot of people are enjoying these talks to get some more detail, get another point of view.
I hope
And
so too.
so,
Give it a good title so people will actually watch. I
I
noticed
always
that
do.
some of your titles, like the ones on special relativity, those are the ones everybody gets excited about.
Well, no, actually, it turns out that if you do put stuff that's in that, like, being talked about now, that's what I found, because YouTube has a lot
Yeah,
of good stuff, and if you
yeah.
put anything like, the E drive, or no, the ME drive, EM
Yeah.
drive, sorry.
Maybe we should talk about the physics of Trump or something like
Yeah,
that. That might get
no,
more
no, no, no,
viewers.
no, no. That's no problem. No, I mean, no physics, no, forget the politics. We're okay. But anyways,
Yeah.
thank you so much. And remember, everybody, don't listen to me or Greg. Read the books, read the things that we're talking about, and you just stay critical and thinking, and you'll find. And I'm your science therapist, and now I'm trying to bring you to other people who can also help you. And Greg is certainly one of those. He may get you a little, therapists get you a little screwed up sometimes, because the way to get you unscrewed up is to scramble you a little bit. But I really appreciate it. And thank you so much, Greg, and have a good night. Hey, ciao for now.